This is last office hours, huh?
Are you doing office hours during?
I'll do office hours on I'll do my Monday office hours still. So we'll have office hours Monday of finals week. Speaking of finals, let's go ahead and we got some questions. Let's talk about the final. What did you want to know about the final? Come on in, grab a chair.
It's more just like in chemistry as a whole, I'm pretty good at like using the equations and knowing what they mean and everything like that.
Mm-hmm.
It's more of like the conceptual questions that I kind of get hung up on.
Yeah.
And I was just wondering like what you would recommend studying or like doing to prepare for that.
You know what I'm going to say?
The book.
Key terms and definitions in particular, right? So essentially, and this happens a lot in my 125 classes, my 124 classes. It's the opposite problem in my 128 classes. So 125 and 128 cover almost identical content, but the places where people have difficulty in that content is different. The 128 folks they have a lot of trouble with the mathematics, but they do way better with the concepts and connecting ideas. My 125 class is kind of the opposite. You guys knock the math out of the park, no problem with the math. But the concepts and how it connects together, like if you essentially, the mentality I see it with is something that I used to have as well, where it's like, if I can't write an equation down to explain it, I can't make sense of it, right? And the problem is we end up with these ideas. Let's pick a concept. We'll do the one that we were doing yesterday in class. It will relate to some of these other things, right? We've got natural log of k is equal to negative EA over R 1 over T plus natural log of A. Right? Mathematically, people have no trouble throwing numbers into there and cranking through it. Conceptually explaining why this equation works and what A means, how it relates to this, right? People can do the definition of A as the Arrhenius constant, but then explaining what the function of it is and why it's important becomes the difficult part, right? And if you look up the definition of the Arrhenius constant, it doesn't have that kind of why is it important, right? It doesn't have that. So like the key terms and definitions is the first step. I guess, are any of you familiar with Bloom's taxonomy? I have the book that's got it on the cover.
Is that where like you have to create, analyze, like?
Yeah, so Bloom's taxonomy is essentially this like hierarchy of learning. And this is also part of why high school is easier than college. I actually want to look it up so I don't get it wrong. Because I will get it wrong. I don't have it memorized. Right? High school is that. Right? The process of learning starts with remembering things. In high school, if you can remember stuff, 4.0, no problem. As we start to get more complicated, right? College is essentially completely operating here, especially in these earlier oh wait. I said I'd get it wrong. Apply. Right? College, our freshman classes are almost all operating here in terms of understanding and applying. So when I say key terms and definitions, I've been stressing key terms and definitions since day one, right? And in key terms and definitions, once we remember them, that's not the only thing we have to do with those key terms and definitions. We have to start seeing how those key terms and definitions relate to each other, how they connect to each other, how they give us this broader understanding. Once you understand once you have the definition for the Arrhenius constant, once you have the definition for the rate constant, once you have the definition for activation energy, then this equation starts to make more sense in terms of how those separate definitions relate to each other to give us this broader overall idea. And once we have that understanding of those separate ideas being connected through this mathematical equation, that's where we can start to do the apply work. We touch a little bit into the analyze work as well, but we don't really get into the analyze work until we get to our upper division classes. We do some of that, right? Like we're doing that with our data analysis and things like that. But I'm not giving you this equation and being like, explain this whole equation to me. That would be like an analyze. I'm encouraging us to think about that, right? To kind of have like some level of all three of these. But with high school pretty much only operating down here, the skills, the study habits we need, the skills we're developing for success have to be really different from what we did in high school. Because the intellectual level at which we are operating is different from what we were doing in high school. Just remembering things. So like a lot of people come to me, especially in week 10, and they say, I've been studying for this class like 30 hours a week and I'm still doing bad. And my question becomes, well, how are you studying? Because if you're doing 30 hours a week in this class, you should be getting an A, no problem. But how you're studying, how you're spending that time, if you're just trying to remember everything, it's not going to work. Right? That's not where success comes in university level classes. Right? You have to be putting study time into understanding, applying, and analyzing. You have to be doing those higher levels. So the big problem is there's good news and bad news here. Good news is you've been working on that all quarter. You've been getting little bits of it. The bad news is late in the quarter for kind of changing the way we're approaching. It's not too late. We can change. Just be nice if we had more time before the final to change our approach. We need to spend more time looking at the definitions and kind of understanding how the definitions relate to each other. Right? How does the Arrhenius factor relate to the rate constants? How does activation energy relate to the rate constant? How do these different terms actually relate to each other? And more importantly, what do they tell us about a chemical reaction? Because we're doing this in the context of a chemistry class, what does that tell us about a chemical reaction? And so having those kind of like, I should have done more of those writing assignments, but kind of doing those writings. Do you have a study group?
No.
Find people to study with. This should be a study group. All of you should just be a study group because you're all here in office hours. You all want to pass. You all want to do well. Right? You could form a study group with other people in the class too, but we got, what, a week until our final?
Yeah.
About? Yeah, a week from yesterday or a week from tomorrow, depending which class you're in. There's still a lot of time to study, and having people who are going to encourage you to study, who are going to text you to be like, hey, let's study this weekend, rather than, hey, let's go to the beach this weekend. I don't think it's a good weekend to go to the beach. It's going to be rainy. But finding those people who are like, it's raining, let's study. And sitting down and trying to explain this equation, not just in terms of how you define each thing, but in terms of its significance inside of a chemical reaction. How does each thing relate to a chemical reaction? That's going to get to these kind of understand, apply, and analyze levels of thinking. It's really difficult to study this material on your own unless you're writing little stories to yourself, which is not a bad idea to do as well. One of my other big things, I'm going to erase this if that's okay. One of the other important things that I think for studying, not just for this class, and the reason I like that, and the next thing I'm going to tell you is, it's not just for this class. It's pretty much every college class you have, that kind of breaking down of what level of thinking am I doing? Am I just focusing on remembering stuff? Am I actually trying to understand and apply this stuff? How much analyzing am I doing? What level of intellectual kind of understanding am I engaging with? Same thing for how we prep for exams. There's a phrase I learned from a sociology, psychology podcast. I think I need two S's there, don't I? right? Practice in the form of the assessment. So if this was a public speaking class, and our final exam was you had to stand up and talk for 5 minutes about a chemistry topic, you would study in a very different way than you would study for a written exam. Right? You'd want to write a little script and you'd want to practice saying it out loud because that's the form of the assessment. You've got to practice speaking it, preferably in front of some people so you can get used to standing in front of people. Our exams in this class are written. They're closed book, they're closed note. They have a time limit. And they're questions that you don't get to pick. They're questions that are essentially new to you. They're questions we've worked on before, they're questions we've done before, but they are questions that you haven't seen. When you sit down to do them, it's the first time you're seeing them. So when you go to study for the final exam, you want to study like this. You want to study writing. You want to do it in a written way. You want to do it closed book, closed note. You want to close your notes, see how much you can do. You want a time limit, and you want to do questions that somebody else picked for you. This is where studying with people, having, even if you don't all make a study group right now, which I still strongly encourage you do, having somebody who will just tomorrow night text you a picture of 4 problems and be like, here's your quiz. Go do it right now. It should take you 30 minutes. Right? And you do that for somebody else. You pick 4 questions. You don't have to make them up. You just, from the homework, from the textbook, from the lecture slides, from the internet, you pick 4 questions that you think are relevant to the class, an easy, 2 mediums, and a hard, and you send it to them and you're like, here's your mock quiz. You got 30 minutes, go. Right? A little bit stressful, but the whole point is we want to practice these things. So that way when we are working on the test, we're used to working in a time limit. When we're working on the test, we're used to working closed book, closed note. Right? We want to be comfortable with this before we get to the exam. Does that make sense?
Mm-hmm.
Those are both, it's a really good practice, it's a really powerful way to practice. If you got other classes, if you're writing an essay for your final, I don't know if you're taking history classes, English classes, you got to get that blue book and you got to write an essay. I never did this, and I probably would have had much better grades if I did. Practice writing an essay. Right? You don't know what the essay topic you're going to get for the final is usually, but you got an hour to write a 500-word essay, 2,000-word essay, something like that. What would you write? Practice writing. Get good at writing. You'll do better on your final. So practice in the form of the assessment. If it was a fitness class and you had to go run for a mile, you're not going to watch videos of people running and be like, cool, I got this. Right? You're going to practice running. So in any of your classes in the future, always think, what's the form of the assessment? How do I practice in that form of the assessment? And the reason I thought of this was because, writing down an explanation of something like this would be useful because we have a written test. But usually I find that a lot of understanding comes from talking it through with people before we try writing it down. So that's where having a study group, even if it's there's 2, 4, 6 of you, right? So one of the most powerful things you could do for studying is the 6 of you say, okay, we're going to do a study group Friday afternoon. The 6 of us are going to get together. Each of us has a different topic or equation we have to explain in 10 minutes. And you just each take a turn. You plan on it taking 8 minutes for each person with questions. And that's an incredible way to study. It's not in the form of the assessment, so that's only a first step. Then you have to try to do these things. But that would be an incredible way to study, especially since you were asking particularly about those more conceptual problems. That would be a really powerful way to study those conceptual problems. Does it make sense?
Yeah.
It gives you some stuff to think about?
Mm-hmm.
Okay, cool.
Thank you.
Questions about that? Yeah.
Is the final like the same like format as like the midterm?
Yep. Multiple choice, free response, 3 hours. No online portion.
And then also, I know like a couple of my professors are doing this, but like half of the midterm is like what we kind of learned since week 8, and then the other half is like the first and second midterm.
It's not going to be quite that for me. So this gets to how are you spending your time. I'm of the opinion that the final examination should be representative of how much we spent on each topic. So you can kind of do a breakdown. How many weeks did we spend on kinetics? 2 weeks. So that's going to be 20% of the exam. Maybe it's going to be closer to 25-30% because we've never had an exam on it before. How much time did we spend on calorimetry?
3 weeks.
Calorimetry? Like a week and a half. You're getting calorimetry and thermodynamics mixed up because calorimetry kind of bled right into thermodynamics. Calorimetry is just Q's, MC delta T and delta H. Thermodynamics is delta H Gibbs energy, delta H of reaction, Hess's law, right? So calorimetry by itself, which is just water heats up, water cools off, Y. We spend about a week, maybe a week and a half on that, so that should be like 10 to 15% of the exam. Right? And so we can just kind of do that assessment of how much time did we spend on it in class. That's how much it should be represented on the exam.
So we spent like the longest time on equilibrium, right? Or like the
Out of each topic, yeah, we probably spent like 2-ish weeks, 2.5 weeks on equilibrium. It's difficult to put a cut on that because we had the spontaneous, non-spontaneous Gibbs free energy kind of lead into equilibrium, which led into like equilibrium's kind of sprinkled through everything since we learned about it. So depends on how you delineate the different topics. But yeah, let's see, what's it? How long did we spend on colligative properties? Oh, I thought it was less than that.
wasn't very
just
long.
Was it like 2 classes?
Yeah, it was like a class and a half. I mean, most of that time was like, it was like a class because of the lab.
Yeah.
It was like 2 half classes, in my opinion. It was like the end of one class and the beginning of another class. So that's going to be like 5% of the exam. Right? We can kind of do that. And that's my opinion for how an exam should be representative of what we did. Again, with a little bit of extra on the newer material because it's my only time to ask you about kinetics. So instead of it being 20%, maybe it ends up being 30%. Okay. Let's do the question 2 from exam, and then we'll talk about the lab. Sound good?
Yeah.
Okay. I'm going to erase this. Let's look at question 2 from the exam. This is the online portion of exam 2, question 4.
So you're given the reaction Ag2CO3 solid goes to 2Ag plus aqueous plus CO3 2 minus aqueous with a K value of 8.1 times 10 to the negative 12. And then you have to calculate the non-standard Gibbs energy for the reaction at 25 Celsius when the concentration of silver ions is 84.3 micromolar, and then the concentration of carbonate is 12.1 micromolarity.
Okay. And you said you had a particular question about this?
Yeah, I was kind of confused, like between like using the two the formula where it's where is it? Oh, the standard G equals, or no, non-standard G equals standard G plus RT LNQ, and then just using and then the that one.
Same.
Yeah. Well, if you use both, would you still get the same answer?
Well, so we should. What's the definition of delta G standard?
Equilibrium, like it happens at.
Oh, I meant the equation.
Oh, that.
right? So if I plug that in for that, I just get those two things are exactly the same because of the rule of natural logs. So let's go ahead and do that real quick, and you can see that it comes out exactly the same. So if I plug this equation into there, I would get delta G is equal to negative RT ln KEQ plus RT ln Q. I can factor out the RT. I'm going to leave this as a negative, and if I've got natural log of Q minus natural log of KEQ, that's going to be Q over KEQ. So I'm going to get RT natural log of Q over KEQ. They're exactly the same. Which one we use depends on what we're doing. If we were using this one, where are you going to get delta G standard from? You're going to get delta G standard from the K value, which means you're doing this anyway. You're just doing it with more mathematical steps.
Mm-hmm.
You should still get the same answer. It's just going to take you longer.
Yeah, that was I think my main question.
Cool. Yep. So we can set up our Q value. So in this, we know KEQ, we know temperature, we know R. All we have to do is recognize that our Q value is going to be products over reactants. So it's going to be that Ag plus squared times that CO3 2 minus. Plug that number in there, that number in there. That'll get me my Q. Then regardless of which form I wanted to use, I should get the same thing. I feel like doing it with this one, you might, like, the big difference between these is doing natural log twice, you might have bigger rounding errors.
Mm-hmm.
I don't think it'll be enough to throw it out of 5%, but it's something to be aware of. Okay. Okay, see. Let's go ahead, we're going to look at some 10.1 problems, and we're at some 10.2 problems, and then it's nap time. My head is just like a little bit foggy. My sinuses are a little bit, ugh. So, okay, 10.1, number 11.
So consider this reaction: A plus B goes to P, and then it's kind of long. So first we run the reaction with initial concentration B equals 0.1 molarity, and then A equals 1 micromolarity. We graph 1 over A as the function of time in seconds and find that the data forms a straight line. The equation y equals 0.0627x plus 2.0522.
2.0522?
Yeah. It's 0.627. We run the reaction again, but this time with the initial concentration A equals 0.1 molarity and B equals 1 micromolarity. We graph the natural log of B as a function of time and find that the data forms a straight line. And then, so what I was having trouble with is, like, it asks you to find the value of the rate constant, but it's not the, like, it's not the slope of what they give you in that equation.
Nope.
So
What's the slope they give you for the second one?
they didn't give you, like, a slope.
It's not slope.
So I was able to get the rate, the orders of the reaction. Like
Okay.
it said that A was the second order, and B was first order. And then it's what is the value of the rate constant, and I just wasn't sure how to like figure that out with the information given to me because I just have like.
So, what are we missing?
The integrated.
It's something to do with the integrated rate law. Let's do it, since we've only got the equation when A is our variable, let's do it for that one. So let's go ahead and write down, so what's going on with these concentrations?
What do you mean, like?
You tell me. What's going on with those concentrations?
Like in the sense of what? Like, what do you mean, like?
What do
Well,
you
okay,
see?
so for the
What
first
do you
one-
see?
Well, I guess they just give us two different ones to like tell us what the order is, like when.
What do you see particularly about those two different ones?
Well, for the first one, oh, okay, because they want you to, like, it's like pseudo rate law.
That's what I wanted.
Because like 1 micromolarity compared to 0.1 is like way less. So they're like telling you that in the first reaction, like B is like, well, I guess depending, I guess maybe this isn't related to slow and fast, but B is like what's determining the rate law maybe, and then the second one
So,
A is determining.
Once we realize that it's pseudo order, was that what you were going to say as well? Yeah, right. So once we realize that it's pseudo order, that concentration of B is going to be approximately constant. I can look at that and I can say, okay, K times B is going to be some new, to get that plot, K times B is going to be my constant, not K by itself. So now once I've got this as my rate law, right, my pseudo rate law, I can go ahead and I can write down what's that plot relate to, y equals mx plus b, for what equation? Right, that's going to be 1 over a of t is equal to k obs t plus 1 over a 0. I'm surprised that it got 0.20522 because that doesn't make sense with our A naught. My guess is that it's got some randomly generated numbers for that because that's weird. Did I write that? It was 2.0522 for the equation that it gave you?
Yeah, 2.0522.
Weird. My guess is this is a randomly generated equation. That's not actually, because 1 over A naught is not equal to 2.0522. So that's weird. But in any case, the important part here is that slope is not the K value, it's the K observed value. So what we need to do is we need to relate that K observed value back to our K value, where we're going to have K observed is equal to our K value times our B concentration to whatever order it has, but we've already figured out it's an order of 1. So it's going to be K times B to the 1. So you're going to take that slope divided by the concentration of B divided by 0.1, you're going to get 6.27 for your answer. Do you see it?
Can you say that one more time? You do.
You tell me.
Okay, so you just divide it by the molarity and you get K? The molarity of B?
Yeah.
Okay. I feel like I did that. Let me try again. Because I remember you went over this in class. So
Yeah, so
maybe I did.
because originally what you told me was it wasn't the slope. And that's because we have to modify the slope, right? The slope is not the K value, it's the K observed value. And so recognizing that becomes the important part.
So what's the like difference between K observed and K, the actual K?
You tell me. I've noticed you ask a lot of questions that I think you know the answers to because you don't feel confident in them. And I'm trying to get you to just say it because I know, because you're smart, you know these things.
Well, okay, is the K observed, is that like, well, because it's like pseudo rate law, like the concentration of B is like constant, it like takes over the K in K observed, or it takes over the slope, or like it's like what this what mainly contributes to the slope is the B concentration.
Not mainly, but it's a multiplicative contribution, right? So our K value is just our K value. So that's correct. You said it right. The language was a little chunky, but it was right. You had the right idea, right? Our K value is our fundamental constant. It's our rate constant. K observed is a modification of our rate constant by other constant things like the concentration of B inside of the process. So since the concentration of B is constant, we can rope it in and we can say our rate constant times our other constant things gives us this observable. What's interesting about K observed is I can change K observed by changing the concentration of B. The rate constant is still going to be the rate constant. But I can change the K observed experimentally by changing the concentration of B. If I used 0.2 instead of 0.1, my K observed would change. See ya.
Bye, thank you.
My K value would still be the same, but my K observed would change.
So, does this only happen, like having a K observed, does that only happen when you have like such a strong presence of one concentration versus the other?
Yes.
Okay, so but if they were like equal, then would the slope be like not K observed, it would just be the K? Or would
Yes.
it still be, okay.
Right, so if the K observed only comes up in the pseudo rate law where one concentration is much larger than the other.
Okay.
Question?
I'm confused on how you're relating like the last two equations when you're solving for the true K value with the K observed value. Like relating the integrated rate with the K observed.
Oh, so this is a definition from up here, right? This is
Right.
That's from up there. The integrated rate law, so once we rewrite it like this, where it's K observed times A squared, that's how we get the first linear plot with the equation for the line. And once we have, right, so I need to find how do I relate my concentration of A in time to this. And that's going to have K observed, right? There's no concentration of B in that first plot.
Okay.
So where's the concentration for B gone? It's hidden inside of K observed.
Okay.
Right, concentration for B is still important in terms of the rate of reaction, but we can hide it inside of K observed as a constant because concentration of B is approximately constant.
Okay.
So this one is wrong.
Is it possible that we've missed some other detail? May I see?
Yeah. Oh wait. Hold on. Actually. Oh no, yeah, it's still wrong.
Okay, so. Okay. First we react B with that. We get a graph that's linear with that. Some similarity. What are the units of the rate constant? That's third orders. That should be 3 seconds and 2 molarities. That's correct. Seconds. Find that from a straight line. The equation is y equals 0.0627. I'm off by a 0 on my plot. It should be 0.627.
Oh.
I just wrote it down wrong. That happens when we're reading fast. And it's going to be different for those of you watching. It's going to be different. You have a different randomly generated number, so check your random generated numbers. Is that it?
Yeah.
Yeah, so sorry about that typo on my part. That's number 11. Did you have anything you wanted to add to our list, or?
No, I was just gonna watch.
Cool, okay. Let's go on to number 12. This is on 10.1.
Dr. Erker?
Yeah.
I had a couple of questions to add from the 9.2.
Yeah. 9.2?
Yeah.
Which ones?
Problem 12. And then 9. The main ones.
12 and 9, okay. We'll get to those. We'll finish the 10.1 questions, then we'll do the 9.2, then we'll get to 10.2.
I have to go to class, but 4:30 I'll come back.
Sounds good.
Okay.
I'll see you then.
Thank you.
Okay. Let's go.
Can I ask you a quick conceptual question about
About this?
No.
Okay.
About the Arrhenius equation.
Sure.
So as you were talking about like, oh, you should know what these. I realized like I don't really know what the A is in the Arrhenius equation, where it's like K equals A times E to the power of EA. Like I know what activation energy is, but I don't think I really know what.
I'll add it to 10.2 questions because I think it'll come up there.
Yeah.
But yeah, we can definitely talk about that. Let's get number 12 out of the way, though.
Okay. This one's about reaction mechanisms.
Cool. Whoa, really?
Yeah.
Okay.
I
What's it
watched some
say?
videos about it, so I kind of understand.
Yeah, we haven't
but-
gotten to that in
Yeah,
class
but
yet.
so if you want
Go ahead.
Okay, so consider the endothermic reaction. 2A goes towards B. And I don't know, actually maybe that's what I missed, that it's endothermic, I don't know. But like, okay, so it has the following mechanism. So step 1 is A goes to X. And then step 2 is X plus A goes to B. And then it says, given that K1 is way less, or like less than K2, do these things on paper before answering the question that follow. Sketch the reaction coordinate diagram.
Okay, so let me think for a second. K1 is much, much less than K2. So that means this is fast. And this is slow. Okay.
And then sketch the reaction coordinate diagram. Sketch the concentration as a function of time for each species on one graph, and derive the overall rate equation. And it's how many transition states are present. I got that one because it's just 2, right?
Yep.
And then on the reaction coordinate diagram you sketched, where are the products relative to reactants, and what is the order of the overall reaction with respect to A?
Okay, so a bunch of things there.
So when it says, oh sorry.
This is how I would sketch it, right? My first step is bigger, that's the slow step. My second step is smaller, that's the fast step. My products end up higher than my reactants. That's because my delta H is greater than 0.
Could you go over like how you like draw it? Like how you, I guess you kind of just did, but like
I
how,
just did, yeah.
yeah, but like is that what like the diagrams are supposed to look like? Like kind of like
This
like a
is,
curve,
yeah,
or-
this is a possibility, right? So what we looked at so far in classes, we looked at something that only had one step.
And that
this would
hump is
be-
the activation energy.
Well,
or like
so-
from the second like part to the there like that distance of the activation.
That's the activation energy.
Oh, from the bottom to the top.
From the bottom to the top.
Okay.
From the reactants to the top of the peak is the activation energy. So for this one, we kind of have 2 activation energies, from this bottom to the top and then from that bottom to the top. Bigger activation energy, slower reaction.
Mm-hmm.
That's why, you know, this K being much, much smaller than this K tells me this must have a much bigger activation energy than this one. Hey.
So when you say that like a bigger activation energy is a slower reaction, is that because it takes like you have to like have more energy available for that like reaction to happen? But so
Right.
like why does that mean that it like that it's slow?
Doesn't that mean that it requires more energy to like go through that reaction? Like it has to need that energy.
There's a couple different things that it means, right? So there's a different minimum energy for the reaction to happen, right? So we can think about it in terms of, like there's future thermodynamics classes will relate activation. I don't think you're taking future thermodynamics classes, but if you take future thermodynamics classes in chemistry, we relate that activation energy to the idea of spontaneous, non-spontaneous, delta G, delta H, delta S. For us right now, we're just saying there's some activation energy. There's a minimum energy we need to hit, and then how much energy we have over that will make this go fast, like temperature, right? The higher and higher the temperature, the faster and faster we can get over that activation energy. So we'll have enough energy that we can jump over it. So, as the activation energy gets bigger, this is going to become a smaller and smaller multiplier, which means K is going to get smaller. Which means our rate gets slower as activation goes up.
So the way the rate constant like contributes to like the overall rate equation, I guess like so that rate constant, I guess I never really knew what the rate constant really was doing. I just knew it was part of it. So like now that you're saying this, like is like the rate or the rate constant is like I don't know, I guess it's helping the reaction move along, or it's like part of determining how long the reaction like proceeds because of like it takes into account the activation energy and the temperature.
Yeah. So previously when we first, yes, but some extra details. When we first learned about the rate constant, when we first learned about rate law, so we learned about rate, we said, cool, there's a rate, we can observe a rate. but we know it's changing with the concentrations. It would be nice if we could figure out how the concentrations were changing it. So we said rate was proportional to concentration by some constant K. So we would write down something like, rate is equal to A, but it's not exactly equal to A because it's going to be, so as concentration goes down, rate goes down, but it's not a 1-to-1 ratio. So we throw in some constant to say,
that makes up for it?
That makes up for it.
Okay.
So if the concentration drops by a half and the rate drops by a half, that's great, but the rate is not going to be equal to the concentration. So the rate constant is this experimental piece that kind of explains how fast or slow a reaction is going to go, and then concentration is the modification to it, right? So increased concentration increases rate. The rate constant really tells us how fast it's going to go. Now, when we start to dig into what that rate constant really means, we say, well, what does the rate constant really mean in terms of, like, how does it tell us how fast a reaction happens? And that's where we get into this idea of the temperature versus the activation energy to see if the particles have enough kinetic energy to overcome that activation energy, and then the Arrhenius factor for the symmetry of the reactants. And you'd be like, is it going to happen? Is it going to happen 100% every time the particles run into each other, 100% reaction? That would be an A of 1. Does it only happen half of the time, depending on the direction of collision? That would be like an A of a half.
Okay,
So this kind of encodes something about the probability of reaction, the orientation of the molecules, the collision idea. Like, do the particles react every time they collide, or do they need to collide in a particular way to react?
So K is made up, is like, that's what it's making up for, that the concentrations can't account for in like the rate.
Exactly.
Okay. And then
Exactly.
so, and all those factors are like the collision, the activation energy, and like the heat, or like the temperature?
Yeah.
Okay. Okay. So the K isn't affected actually by like a factor of K isn't concentration, right?
Correct.
Okay. But
Right?
we can
That's
just
why
use
we
the
have to have
concentration.
concentration in there
Yeah,
as
but
well.
we can just use the concentrations to find K. Okay.
Yeah.
And like that reaction, like 2A goes to B, the 2 in front of the A doesn't really affect any of the rate or like the rate laws.
Correct.
Okay.
But 1 and 2 are elementary, so when you write their rate laws, you can use those coefficients,
Correct.
right?
So we haven't gotten to problems like this yet, but when we start proposing how does the reaction happen in like what's called elementary steps, like, like A first turns into compound X and then X and A react to form B, when we start proposing mechanisms, then we can use the molecularity of the mechanism to say how many molecules are colliding for this reaction to happen. That gives us a way to talk about the law of the individual steps. Now, any mechanism we propose has to match the experimentally determined rate law. Right? Mechanisms are made up things for us to try and explain the rate laws. The rate laws are experimentally determined. Those are real. Our proposed mechanisms are our best guess at why those things are happening.
But we haven't like really touched on that yet.
No, not unless you've been reading ahead in the textbook, which I strongly recommend.
Okay.
Always recommend.
And then with those graphs, that's like the reaction occurs, right? Because it starts off lower, and then when the reaction finishes, it's like the delta H is higher.
So that's part of what makes it an endothermic reaction.
Okay.
So this was a particular example that was an endothermic reaction happening in 2 steps, where 1 step was slow, 1 step was fast. The first step from reactants over was slow. The second step from reactants from intermediate to products was fast.
So because it said like K1 is like far less than K2, is that how you determine that the first one is slow and the second one is fast?
Precisely.
So it's like so the first mechanism is related to K1 and the second mechanism is related to K2.
Together is the mechanism.
Oh, sorry, the steps.
Step, yes.
Yeah.
The first step is K1, is K for step 1. K for step 2 is K1, K2.
Okay, so that's how that's telling you the slow versus.
Mm-hmm.
And then when it's like, when the first one is slow, that means that that's the like rate order or something? No, that's the
Rate determining
rate
step.
determining.
Rate
step.
determining step.
Oh yeah. Okay. So back to the questions.
Uh-huh.
So okay. So on the reaction coordinate diagram section, where are the products relative? So because it's endothermic, like that's why our products, like, is that why they end up above the reactants? If we was
Precisely.
exothermic, it would be below.
Yep.
So what does that mean in terms of like it's above or it's below? Like does that mean there's more product, or like what does that mean? On
Exothermic versus endothermic.
Oh, that's just
Yep.
what it is. Okay.
This
But
is an endothermic reaction.
But it doesn't like correlate to amount of products or anything like that?
Nope. Right, so if we put an axis on this side, this is an energy axis, not not an amount, not a number of moles axis.
Okay. So so by having the products like they're higher because it's endothermic, it's saying that like we have more energy than we started with, or it's not saying that.
No, energy is needed overall.
Oh,
Right?
this is like energy needed.
Yeah.
Okay.
Right, so this is an endothermic reaction. Energy needs to be put in to make this reaction happen overall.
So it's saying like there's more energy needed to get to the products than I guess just having the reactants exist, or like what is like it being.
So this don't overcomplicate it.
Okay.
This is the same endothermic exothermic that we did back in week 2. Delta H is positive. That's all it means.
Okay.
Right? Delta H is positive. It's endothermic. We could then try to say something about delta S and delta G if we wanted to, but that's not what the problem's getting into. It's just delta H is positive.
Okay. And then, so how do we determine the overall order with respect to A? Is that just like the rate determining step? Or?
Yeah.
Okay.
So in this situation, since the slow step is the first step, and that's the rate determining step, I would just write this, rate equals Ka. And it's first order with respect to A. In this proposed mechanism that I hope is real, right? It has to match. Is this the correct mechanism for this reaction? I don't know. I can never prove that it's correct. All I can say is that it's consistent with the observed rate law. We're going to do this tomorrow in class as well. That's all we can say is it's consistent with the observed rate law. Or if I propose something that was bad, I could say it's inconsistent with the proposed rate law. This cannot be the mechanism.
How would you know if it's inconsistent?
If we measure the rate law, the rate was Ka squared.
Oh, like
that's not this,
okay.
right? So this is proposed.
It's like.
And then it just has to match with observed, experimentally observed. And if it doesn't match, then it's inconsistent.
So like since the first step is slow, like we say that that's the determining rate order, is that kind of related to pseudo rate order where it's like because it's so much that it
Not quite.
Okay.
There's a different, when we get into mechanisms, there's a different approximation we use if the first step was fast and the second step was slow, called the steady state approximation.
Right. Okay. That's it for this one.
Okay.
And then I think problem 15 is not really one you can do on the board, so maybe we can skip it. It's like oh, put this data into Excel and then like.
Oh, that would be challenging.
Yeah. So.
Yeah. So number 15, do on your own. Make a graph. We'll look at it together in just a moment.
Okay. And then
10E. Did we just go over that? No, that was number 12 we just did.
So this one was conceptual questions.
Okay.
10E. So.
Oh wait, any questions about this before I erase? (10E).
Okay, so for a reaction where delta G standard is positive, is the forward or reverse reaction activation energy larger? Is the forward or reverse rate faster? And then does your answer for B change if you're at equilibrium? I just don't know how to relate delta G standard and like activation energy really.
Mm.
That was like I think.
So what does delta G standard tell us?
Tells us like how likely a reaction is to occur.
Not
That's what it used to
exactly.
be. Or it's like, or wait. Yeah.
So if delta G is greater than 0, this would be reactant favored. So I would want it to be easier to get to reactants than to get to products. So if here are my reactants, and here are my products, I want it to be easy, well, let's change this. I want it to be easier to get to reactants than to products. So I might do something like this. Right? For this to go backwards, for the products to get to reactants, a little bit of energy to jump over that hump. For the reactants to get to products, very difficult to get back over. So I might make this giant endothermic type reaction. And it kind of makes sense that we do an endothermic, a really big endothermic reaction, because if I remember, delta G equals delta H minus T delta S. If delta G is a big positive, and I make delta H also a big positive, then the T delta S term is not likely going to have a big effect. So I just make my delta H a big positive to make my delta G also a big positive. I can't really say if it's spontaneous or not unless I have that delta S information, but this would be consistent with this kind of observed of delta G greater than 0. Question?
G and H have the same sign. It's hard to. You would have to say that entropy is unknown, right? Unless you have.
We would end up with
anything
an
with the
unknown entropy unless we have information about the temperature. So that's the kind of conceptualization we would have there. We'd look at the delta G. Because we know the difference from the reactants to products is going to give us some delta H information. We've got the delta G information. I can relate delta G to delta H.
So is like forward reaction versus reverse reaction? Is forward just like the going like
Reactants to products.
and then products to reactants?
Reverse is just products to reactants. So I would say I've got a massive activation energy for the forward reaction and a small activation energy for the reverse reaction. It would be something like an endothermic reaction, a massively endothermic reaction to guarantee delta G is positive.
And then the next question is the forward or reverse rate faster? So is that the same thing?
Which do you think is going to be faster, going that way over this giant activation energy barrier or back over the small activation energy barrier?
Reverse reaction is gonna.
Reverse reaction should be faster.
Yeah. Okay.
Yeah, the reverse rate should be faster. And we can relate that again back to the Arrhenius equation, because we've got K equals A e to the minus EA over RT. That bigger activation energy, that smaller activation energy is going to affect the rate.
So like you have two different activation energies for like reversing and going forward.
Yeah.
How do you like, or I don't know if that's like something we do, but like how would you find like the difference in those energies, or is it like, are they related? Or?
So they are related. What are the two things that relate them?
Like that big gap.
Let's say this is the EA of the reverse reaction. How would I relate it to the EA of the forward reaction? What would this be?
That would be the forward reaction.
Not quite. The forward reaction would be all the way to the top. From reactants to products. It's the delta H. So the delta H and the EA. So the forward reaction So the activation energy of the forward would be this delta H plus that reverse energy. Okay, just relate them.
And then does this change if we're at equilibrium?
So if we're at equilibrium, great question.
I
What
don't
does
know
it
how
mean?
you relate
What does
that.
it mean if we're at equilibrium?
It says like, does your answer for B change if you're at equilibrium?
Which one was the, what was
Is
question
a
B?
forward or reverse rate faster?
Right. So what's it mean if we're, what does equilibrium mean about forward and reverse rate?
Well, if your like equilibrium constant, or if KEQ is greater than Q, then you would go to products. I don't know if this is related, but if it's the other way, then it goes to react. Like it's.
Sure.
I
And
don't
at
know.
equilibrium,
And at equilibrium, your Q and KEQ are the same.
yeah.
Yeah.
So what's your rate if Q and KQ are the same? Should anything be changing?
Exactly.
No.
No.
So,
So at equilibrium, your forward and reverse rate must be the same. That's what equilibrium is,
oh right, because it's the okay. Yeah.
right?
Yeah.
So at equilibrium, your forward and reverse rate have to end up being the same. So you have to have enough reactants and small enough products, right? And the way I think about it, this is kind of a silly way to think about it, but I think if I have more and more reactants, I essentially am filling up this side of the container. And if I have enough reactants, a little bit can spill over, but I'm still going to have mostly reactants. But I'm going to get to this point where it's kind of spilling back and forth evenly, and that's equilibrium.
So like I kind of get how we're like relating the two, but I feel like I wouldn't be able to explain it. Do you think you could?
Which part?
Like the part where it's like when it's at equilibrium, like they would be the same.
So it has to do with the definition of equilibrium. The definition of equilibrium is essentially the forward and reverse reaction are happening equally, right? So my amount of reactants, my amount of products is not changing, right? If I'm product favored, that means my reactants towards my rate towards products is faster than my rate towards reactants until I get to the point where I end up with more products than reactants. When I hit equilibrium, it's not going forward, it's going to be balanced between the two, so it looks like nothing is changing. Right? It has to do with the fundamental definition of equilibrium. Right? And this is one of the weird parts about equilibrium, and I tried to stress this a little bit this quarter. Equilibrium does not mean nothing is changing. It means it appears as if nothing is changing because the reaction has balanced out. The reaction is still happening. It's still going backwards and forwards, but it's going backwards and forwards evenly, so that anytime we look at it, our concentrations appear to not change. Bringing in the idea of rate with that, you could just say the forward rate and the reverse rate are the same, so that products and reactants are being equally created and destroyed.
So like forward and reverse rate is like it's the same thing as like, or I don't know if it is the same thing, but is it the same thing as like when we say something is like product favored? It's like when we're saying that like it's like it would be faster to get over like to go to products than it would be to go to reactants, like with the activation
From
energy.
standard conditions, right? So when we talk about like delta G in terms of product favored or reactant favored, that's delta G standard.
Right.
So we have to think about where we're starting from, and from that starting point, the forward rate is faster than the reverse rate. But if we're saying at equilibrium, the forward rate and reverse rate have to be the same, we might still end up with more products or more reactants. This is more reactants, but at equilibrium. But at equilibrium, the rate is going to cancel out. And the definition of equilibrium is the forward rate and reverse rate are the same. Okay, so that's 10E, big conceptual question. Let's go ahead and get those 9.2 questions, and then we'll switch back over to 10.2. And if anyone who's come in wants to add questions before we keep going.
I need to find one. I know
Go for
generally
it.
what I want to talk about,
Okay.
but I need to find a good question.
Is it okay if I erase this and we move on to 9.2? So let's go ahead and look at the 9.2 questions real quick. Starting with number 9.
Sure. So it says the reaction lowercase a, uppercase a to products is a first order reaction with a rate constant of 2.892 times 10.
What was that rate constant?
2.892 times 10 to the power -4 seconds -1. The first question asks, how long does it take for the initial amount of A to decrease by 35%?
By 35%?
Yeah.
So that would mean our A at time t would be 1 minus 0.35 times our A naught. Whatever we started with, we want to be 35. So we start out 100% A naught. We want to be 35% less than A naught, so we're going to be 0.35 less than A naught. Do you know what to do from there? So this is, for most people, defining this first part is the tricky part. Defining what does 35% A naught less A naught mean is the part that most people have trouble with. Once I write this part down, most people can pretty easily do natural log of A of t is equal to negative kt plus natural log of A naught. Plug in my definition for A naught, that's going to just be 0.65. So I'm going to have natural log of 0.65 A naught. I'm going to drop the brackets. I'm going to go ahead and subtract my natural log of A naught over here. And that's going to be equal to negative kt. Yeah?
Yeah.
And then we're just doing algebra at that point. Notice the nice part here is because of the rule of natural logs and the fact that it's first order, I can just get natural log of 0.65 A naught divided by A naught is equal to negative kt. Notice my A naught's going to cancel out. I'm just going to get the natural log of 0.65 is equal to negative kt. This is going to give me a negative number. I'm going to divide by negative k. That'll get me my t. Does that make sense? I did that pretty quick. I did it in office hours yesterday as well, so you can watch the video. But like, did that make sense?
Yes.
Right, and again, here's the important part. It tells us it's first order, so we know we're going to be using this for integrated rate law. It particularly was asking about a change in amount, so we have to do integrated rate law. So we know we're doing this equation. Then the difficult part becomes, I know k, right? I know k. I know A naught. I don't know A naught. I'm being asked, I know k. I'm being asked to find t. I'm asking the time. And then the difficult part becomes, how do I deal with it? It looks like I have two unknown variables. Because I don't know my A of t, and I don't know my A naught. But then it defines the A of t in terms of A naught. Right? It says, I want to find the time when 35% has been removed. So that's going to allow me to plug this definition in. This trick only works with first order. It wouldn't work with 0th order or second order. But with first order, because of the way natural logs work, I get to cancel out my A naught. If this was 0th order or second order, I'd have to give you a specific number for A naught because it's not going to cancel out nicely. First order, we always do this trick. And it's just a mathematical kind of fun thing that comes out of it. That was part A. What's part B?
It just says how much remains after 25 minutes, but I think you just plug in the 25 times. Yeah.
Does it ask us in a fraction?
Enter as a percent.
So essentially we're going to solve, so this was 65% left. We're going to do the same thing. We're just going to solve for what's in this parenthesis in terms of a percent remaining. Or a percent decayed, depending on what it asks for. Percent used or percent remains?
Just says how much remains.
Remains. So this, the 35 is percent used, the 65 is percent remained. Right, so 100 minus 35 gets us the remain.
But
So
you solve for that value and then you just plug in the 25 for t, right? Or,
yep.
But make that seconds.
Mm-hmm. So the other thing we can do once we realize we've got this trick, we can essentially define a new equation, which is percent remained divided by 100 is equal to e to the negative kt. Divide by 100 because it's going to give us the decimal version, not the percent version. And for first order, it's always going to come out like this. And so this is where nuclear radiocarbon dating comes from. Percent remain of C13 or C14 gets us how much time has passed. Population growth and decay can be done with this as well. Like a lot of things. Like I said when we first started doing this, a surprising number of phenomena follow first order rates. A surprising number of phenomena follow first order rates. And so we can model a lot of like how much is left with this idea.
I kind of had a conceptual question relating to this, but
Sure.
for zero order reactions, it's not dependent on concentration, but for first and second, it is dependent on concentration.
We have to be careful with what we mean when we say it is not and it is.
Okay.
Right? So for zeroth order, the rate is not dependent
Right,
on
the rate is not
the initial concentration. But the time it takes to react does depend on the initial concentration.
okay.
Right? And so when we say it does or doesn't, we have to be careful. For a second order, the rate does depend on concentration. So as the reaction proceeds, the rate changes.
Right.
And that means that the half-life does not depend on concentration for first order. So when we say it does or doesn't depend on concentration, we just have to specify what we're talking about.
So you're saying that for first order reactions, the rate does depend on the concentration, but the half-life. Oh, the half-life doesn't include the concentration. It's just the K of the reaction constant. Okay, that makes sense.
Right?
Right.
And so when we say it does or doesn't depend on concentration, we just have to be careful. Are we talking about the rate? Are we talking about the half-life? Are we talking about percent remaining? Right? Each of those things, slightly different ideas, and so we have to be careful with our language there.
That helps.
Cool. Is there a part C?
Yeah, it's just asking for the half-life of the reaction.
Oh,
But
that's pretty
you
easy. If
just
we've
use
got
the
K,
language.
we've got it because
Yeah.
because it's first order. That one's easy.
Yeah, and then
Part C is probably the easiest because it's first order.
okay, yeah, and then it just says for D, it says how long does it take for the initial amount of reaction to decrease by 87%, but that's kind of like part A.
That's part A again.
Okay. Okay.
Cool. Right, and so it all becomes identifying that it's first order, and then what it means, how we can use first order to do percentages. And first order is the only one where we can do this percentage trick because of the natural log rule.
Okay.
The other ones we can do percentage tricks, but they don't come out as nicely. They come out much chunkier.
Okay.
That's number 9. What about number 12? Any questions about this before I erase? Let's look at number 12.
For 12, again, I have to show you it's a graph. But
Oh.
my question was about the initial concentration of A. The initial concentration is the intercept, right?
Yeah. Oh, careful. It's not just the intercept. So I'm going to go ahead and put this on the board for everyone who's at home to see. Right, we've got a plot that's natural log of A versus T. This one cuts through the 0 point. I don't feel like doing that, but you get some straight line, and you get y is equal to
Negative 0.05x plus 1.6094.
right. So right away I can look at this and say, well, this must be first order because natural log of A versus T made a straight line. So I'm going to have natural log of A of T is equal to KT plus natural log of A naught. That means 1.6094 is equal to natural log of A naught. The most common mistake people make is they see this and they say, cool, I'll take the natural log of that number, and that's going to get me A naught. But when you look at this, how do you undo the natural log to get a naught by itself?
Take
E to the power of 1.6094 will get us a naught. And so it's just I do the same mistake. I see this most commonly when we're doing not even this stuff. Not the Beer's Law stuff. Which stuff is it? I can't remember right now. But it's essentially, when we're doing the Gibbs Law stuff. And our slope is like delta H over R, and so people take their slope and divide by R. It's like, no, slope times R so you can get delta H alone. Same thing here, you just got to do E to that.
Okay.
Follow-up questions? What are the next parts of that?
It's the last part was just what is the half-life of the what is the half-life? So you just take the you have the rate constant and then
It's just going to
you
be
just plug that in with the
T1 half is going to be natural log of 2 divided by 0.05.
Alright, there's no initial concentration.
No initial concentration for first order, so it
Okay.
makes it really easy.
Okay, yeah. I think I did that right. I just want to make sure.
Cool. That was it for questions from 9.2.
I had another one if I could see.
Yeah. What time is it? How are we doing the time? Yeah. Oh, yeah. We can do another.
It was 13, and it asked you to find the order, the K observed, and the K.
Oh, the angular acceleration is different.
Any questions on this before I erase?
Oh, the initial velocity you also have to find.
Okay.
Because
Let's get
so
it.
it's still,
Okay, a student has a reaction
so
mixture of
theta
0.169 molarity substance A
0.169 for A.
and then 1.0 millimoles, the lowercase m, yeah, substance B.
And then you have to convert this again into radians.
Milli, not micro?
No.
Okay.
And then it says after the reaction finished, the student plotted the inverse concentration of B in molarity as a function of time in seconds.
Got a straight line?
Yeah, and found that the graph was quite linear with a slope of 1.89 times 10 to the power negative 3 liters per mole seconds. And then suppose that the student knew from other experience that the reaction is third order in A.
Okay.
So the first question asks, what is the order of reaction B? I think that one is fine because the graph tells you that it's the inverse concentration. So it's 2. And then
Cool.
the K observed, I said was the slope of the line. But then when solving for the K, I know you said that's the concentration of B times the K value.
Not in this case.
Oh, okay.
Not in this case. Which one is our constant in this case?
Yeah.
A. So when we write this in our pseudo rate,
No, so okay, so we can write out at least the next line.
this is going to be K times A cubed
Distance traversed
times B, where this is going to become our K observed.
Right.
The initial, which is what you just found, the 31.4 grams per second. Times
So our K observed, which is going to be our slope, is going to be K times A cubed. We know the A value, so we can do K observed
sine of the angular
is
acceleration
equal to K
velocity and
times A cubed.
Okay.
How do you get K alone?
theta double dot.
You just plug in the slope value and then the concentration for A.
Yep.
And divide.
And divide.
Where if
Okay.
you
Don't forget the cube, because apparently we did another experiment where we could figure that out.
Okay. Okay, that makes sense.
Right, and again, the important part here, and I still have to do it in 3 steps like this. I have to think, what's my pseudo order? What are my constants that I can group together? How do I ungroup them? Right, so that's always how I go about the process to make sure I don't mix up which thing is my constant part. Okay. That's it for the questions from 9.2. We ready to do some 10.2 questions? And did anyone who walked in just a little bit ago have specific questions they wanted to add onto the list?
I have a quiz question.
quiz question. Let me erase this.
Actually, me too, but I can ask.
No, let's add it to the list. We'll do it after the 10.2s, but let me put it on the list so I don't forget. Who's got their quiz questions ready?
Oh,
Just to add to the list.
Number 5 on quiz 6.
Yes.
Quiz 6, number 5.
That's delta TP, right?
Quiz 6. Sorry.
Number
No, no, no.
2 on quiz 6.
In that's the one I was thinking of.
Number 2 on quiz 6, okay. And then any questions, specific questions for you?
I'm trying to find a good problem right
Okay.
now still.
No worries.
Yeah, so.
Okay,
Angular
yeah.
acceleration magnitude, so
Still like for
again,
9.2,
you already
question
assigned
8.
this as negative.
Oh, okay.
And this is, you're assuming this is a magnitude, so it should be positive. So what you're looking for.
Okay, let's do number 8 from 9.2. And then should we do 10.2 or quiz questions first? I'm asking you because you had the 10.2 questions. Do you have a preference?
So this is again just going to be.
Maybe we could just do like 1 or 2 of the questions typically,
Sure.
because I think 2 and 10 are similar, so we can just do 10.
Okay,
And I think 10, I kind of know how to do it, but I'm not.
we'll take a look at it. We'll take a look at number 10. So let's do 9.2, then we'll do question 10, and then we'll do quiz 6. Do you feel like you've got a better grip
Yeah,
on the
I
Arrhenius
understand.
constant? We talked about that in one of the previous problems. 9.2, number 8. What is it?
In the gas phase, iodine atoms combine to form I2 in a second order process with a rate constant of 7.0 times 10 to the 9.
Is it second order?
Yes.
With K equal to
7.0 times 10 to the 9.
positive 9?
Yes.
Woo! That's quite a rate.
At 23 degrees Celsius. And then the first part is if initial concentration of I is 0.086, calculate the concentration after 2 minutes.
Okay, how would we even start to do that?
That's what I was lost on.
So there's a couple hints we have here, right? It tells us it's second order. As soon as it tells us it's second order, we can write down a couple things. We can write down rate is equal to K times I squared, right? That's second order with respect to I. And then I can also write down the integrated rate laws. I can write 1 over I at time t is equal to kt plus 1 over I at time 0. Now, the question isn't asking us about rates, it's asking us about amount reacted or amount remaining, right? After a certain amount of time?
Yeah, concentration.
Concentration after a certain amount of time. So which one do you think is going to be more useful to use?
So that last part was.
Second one's going to be more useful. I can plug in my initial concentration, I can plug in my time, I can plug in my rate constant, and I've only got one thing to solve for. Right? Once we get to this point, it's not so bad, but we have to be able to read the vocabulary and see what it's pointing us towards. It tells us it's second order, so I know these are 2 things. I could have written a third thing I know about second order. I could have written T1/2 is equal to 1 over K I naught. But this, and I don't, the reason I write down all 3 is because I don't know which is going to be useful for the problem. It turns out of these 3 things that I knew about second order, only one of them was useful. So once I recognized that's the useful thing, how did I recognize that was useful? The information that was given in the problem versus what it was asking us for. Right? Only one of these equations has an I at time t later, some concentration at a later time. That's why this was the useful one.
And then we would convert that 23 degrees Celsius to Kelvin?
Um,
Does that matter?
doesn't even matter for this problem.
Okay.
The only way that that would matter is if the temperature were changing. But since the temperature is not changing, don't need it. Right? And that's why you'll see a lot of problems that include temperature, but then you don't do anything with the temperature. there's a lot of chemical phenomena where the temperature doesn't matter as long as it's constant. So it's like, temperature's a constant 23 degrees Celsius. It's like, cool, I don't need that then. But if the temperature changed, I would need to take that into account. Okay. Let's hit 10.2 number 10 because you've been waiting really patiently, and then we'll get those quiz questions. Ready? Okay if I erase this? Okay. Did you find a question yet?
Yes. From the slides versus from
Okay.
NFL. So a bit of a throwback. Electrochem, slide 40. And I have the problem, and I want to make like one change to it to kind of better address the thing.
Okay, we'll look at that in just a moment. Cool.
Absolutely, thank you.
Okay, so let's do 10.2 number 10. That one taken care of. What's 10.2 number 10 say?
It's a reaction coordinate diagram.
Okay.
So draw a reaction progress diagram for a reaction at 25 degrees Celsius with an activation energy in the forward direction of 14 kilojoules per mole and an activation energy of 47 kilojoules per mole in the reverse direction.
How far?
What was that, 27 kilojoules?
The first one was 14 kilojoules and the second one is 47.
47.
Label the diagram with the forward and reverse activation energies, the transition state, and the free energy change of the reaction. So I think I kind of understand how to draw it because we did it earlier.
Yeah.
But I think with the specific things it's asking for, I'm like a little bit unsure on what exactly they are.
So we can look at this. Forward is going to be 14. So the forward should be, what is that? That's like a factor of, that's like
It should be easier to
3 times bigger.
Yeah.
So I'll do this, and then I'll do 1, 2, 3, something like that. So putting in some labels, this activation energy, that would be 14. This activation energy would be 47. That means the difference between the two for this is kind of this delta G, delta H idea would be 47 minus 14 would be 33.
Okay, so when it says like
At least, like, maybe you'll see a two-dimensional one.
the free energy change, that's the 33.
Yeah, it's technically a little bit off from free energy. It should be like the enthalpy, right? They're using the same idea that delta G is approximately equal to delta H. Right, so they're essentially saying like this minus T delta S is small. In situations where the T delta S term is small, it gives free energy, your enthalpy can be thought of as pretty much the same, that
Okay.
energy change.
Okay, so yeah, then it says estimate the free energy change of the reaction, so that's just the
That's why it's an estimate, right? Because we're
Okay.
saying that T delta S is small. So the delta G, the free energy, should be about that delta H change.
Okay, and then when we draw these kinds of graphs, do we need to like I notice like a lot of times when you do it, you don't do like
An axis on it?
axis.
Right,
Is
so
that not important? Or
it's
should-
important, but it's kind of intuitive.
Mhm.
That's energy. And this is technically Q, where we only do a Q of 0 and a Q of like infinity, right? So we just do reactants to products. So we do all reactants to all products. We know it's not going to be exactly that, but so we usually just do the energy axis, and that's it. And most people, once you see these, everyone gets really lazy with putting the energy axis on there because they're like, anytime you draw a activation energy diagram like this, it's on an energy axis. But we shouldn't be lazy yet because we're just learning it.
Okay.
Question?
Why are they both positive numbers?
Because it's the positive of the forward or the positive of the reverse,
Okay.
right?
So is it taking energy to go forward and then?
So it would take 14 kilojoules of energy to get the reaction started, but then we'd get a release of 47 kilojoules of energy. So this would be an overall negative 33 because it's an exothermic reaction. So we can relate the two that way. Or we could say it's 47 kilojoules of energy to go backwards to get over that lump. We get 14 back for a net of, that would be a 33 positive if we were going backwards because it'd be endothermic backwards.
Yeah. Okay, that makes sense. I know you have a lot of like more questions to do, so I was wondering, they have like the notebook questions. I was wondering if I could like fill them out and then like send you an email if you could let me know.
Absolutely.
If it's, like,
Yeah,
along
yeah.
the lines of what's right.
Good to do. Let's get these 2 quiz questions done real quick, and then we'll look at this problem from the lecture slides. Who's got quiz 6 number 2 ready? Yeah, let's do it.
Consider this cell AG solid and ion.
Zero order to B.
Whoa.
Everything should always be.
Keep going.
And we have the concentration of the ion, and it's 55 micrograms.
Yeah, remember it's kilograms.
Okay.
And then it's just the same thing except the reverse. The ion.
What's the Ag plus concentration in this case?
1.08 moles.
Okay, so
Molarity.
Oh, identity versus
Okay.
time.
Great.
Yeah.
What's it asking?
The first part is calculate the value of the standard cell potential at 25 degrees Celsius. Okay, and then the second one is calculate the value of the cell potential at 25 degrees Celsius.
and so when this happens, mass 2 is rotating so
Products of reactants. 55. Now, let's do this a little bit slower. I wanted to get it jotted down pretty quickly because I know we're running out of time. But how was I able to do that? Well, so what I think about when I look at this setup is this is solid to reactants Ag plus. This is silver ions to products Ag solid. So if I looked at this in terms of the reaction, it would be Ag plus at 1.08 molarity going to Ag plus at 55 times 10 to the minus 6 molarity. I know my standard cell is 0, so I get my negative RTNF, ln I can tell my n is equal to 1. And when I do products over reactants, there's no squares, there's no cubes, so that all works out fine. My products is the lower concentration, my reactants is the higher concentration. I'm expecting a positive voltage in that case. I can plug those in and get a positive cell potential, right? This is going to give me a negative natural log because it's going to be a really small number. There's going to be a negative times a negative. That's going to get me a positive. So I can go ahead and say E cell is equal to negative 8.314 times, what temperature was this, 25 degrees? 298 divided by 1 times 96485. Natural log of 55 times 10 to the minus 6 divided by 1.08. Plug in the calculator, see what we get. Is this what you did?
Yeah.
What did you get for an answer?
I got 0.2538.
Oh, quantity.
0.1 meters over 1.
Isn't this the one where you can add their molarities together and then divide by 2 because they're the same?
That's if we're asking for the final concentration, not the cell potential.
Oh, sorry.
And then we need to convert this to
Okay, I messed that up because natural log 6 divided by 1.08 is equal to natural log times 8.314 times 298 divided by 96485 equals, what'd you get?
125 3
That's the same thing I got.
I might have got the next. There's another one.
Oh, there's another one. Okay, what's the next one?
Calculate the concentration of ions in the anode half cell when it reaches equilibrium.
Average of the two concentrations.
Okay, I just did the second concentration. That's why.
Ah, so here's what happens, and there's a couple different ways we can go about it. The long kind of proper way to do it is to do an ice table, because we're doing equilibrium. So that's our initial, our change, and our equilibrium. But once we do a couple equilibrium tables for concentration cells, where it's the same thing on both sides, and we've got a standard cell of 0, we see it's going to end up the same. It's going to be minus x plus x. I'm going to get 1.08 minus x. I'm going to get 55 times 10 to the minus 6 plus x. The x is small approximation, does not work here. But my k value is 1. Because it's going to be, right, natural log of k equals RT over NF E cell standard. I might have my NF and my RT mixed up here.
I think that's right.
I think it's supposed to be NF over RT. Doesn't matter because E cell is 0, so it's just going to be natural log of k equals 0. You're going to do e to the 0, that gets you 1. So you're going to get 1 is equal to products over reactants, 55 times 10 to the minus 6 plus x divided by 1.08 minus x. Do a little bit of rearrangement, and you're going to get 1.08 minus x equals 55 times 10 to the minus 6 plus x. I'm going to add that, subtract that. I'm going to get 1.08 minus 55 times 10 to the minus 6 equal to 2x. It always ends up this way, divided by 2. I thought that should be a plus, though. So it's not exactly the average. Unless I was going too fast and I messed up my math someplace.
Okay, but usually it's the average.
Yeah, it's something like the average. I guess it's not the average, it's the midpoint between the two concentrations. So they meet in the middle. But since this is such a small number, it just becomes 1.08 divided by 2. It becomes 5.04. 0.504. Number 5. From quiz 6. I'm going to erase this if that's okay.
I feel like this is probably simpler than I was making it, but
Let's see.
I could not balance the reaction. Balance the following reaction in basic conditions.
Oh. Okay, let's see.
CH3OH liquid CS. Oh, it has like the it's giving you the
Oh.
the what's it called? I'm blanking on the name. Yeah.
Shorthand notation.
Yes. Cu2O solid, and then Cu solid.
Okay, we got to balance a bunch of things. We're going to do I'm going to try to do this pretty quick so I have time to do that last question. CH3OH is going to C solid. I'm going to add H2O. I'm balancing in basic conditions. I'm going to add 2H plus 2 OH minus plus 2 OH minus. I feel like I'm messing up someplace. That's 2, that's 4, that's 2 H pluses. Oh, I added my H pluses to the wrong side, that's why. That's 2H plus 2 OH minus. That's going to get me 2H2O plus 2 OH minus.
Wait, I thought you added the H and the OHs to the left, the other side of the H2O.
Well, so not always, right? I have to balance my hydrogens. When I add my H2Os to balance my oxygens, I still don't have enough hydrogens over here.
Yeah.
So I have to add 2 more H pluses, so I get 4 hydrogens on this side and 4 hydrogens on this side. But I can't add H pluses by itself because it's in basic conditions. So I add the waters. I add 2 waters and 2 hydroxides. So now I've got 2, 4, 6, 4, 5, 6. So I've got my hydrogens balanced. I've got 2, 3 oxygens. I got 1, 2, 3 oxygens. So it's balancing my oxygens. So I'm going to have 2 OH minus plus CH3OH goes to C plus
We don't have
3
to, you don't have to finish.
H2O.
I could balance the C's and the.
Yeah, the second half is easier. But yeah, this is a kind of weird one where we add hydrogens to a side that we don't normally add hydrogens to because of the way the hydrogens
More
balance.
hydrogen- Okay, so
Yeah.
typically you add the hydrogens and the OHs to the opposite side that you add the water to.
In the simple examples we've seen, but you always add the hydrogens and the OHs to the side that needs more hydrogens.
Okay, so you add water to the side that needs oxygens, right?
Yes.
And then after that, you add the H pluses and the OHs to whatever side needs it.
Yes.
And then
And usually that's the opposite side of the
Yeah.
waters because the water adds so much extra hydrogen, but not in this case.
And then on the opposite side that you added the OHs and the H pluses, you add
A balancing number of OHs.
Okay, that makes sense, yeah.
Cool.
Thank you.
A little bit of a tricky one. Okay, speaking of electrochem and balancing in acidic and basic conditions, let's look at slide number 40 real quick. Yeah, we got time.
So originally on slide 40, you were given, actually it was that same equation, the silver plus silver ion going to silver ion and silver.
Oh, cool. So we got AG
I
plus.
picked that specifically so I wouldn't have to worry about E naught, because that would just be 0.
Okay.
So originally you put the 2 concentrations, it was finding the cell potential. I'm normally fine with that. What I'm struggling with is like, given one concentration and a cell potential, get to the other concentration. I am consistently getting that wrong. So I'm originally, it was concentration of the anode is 0.01 molar, concentration of the cathode 1.2 molar with a cell potential of 0.06 volts. And so what I want to do is, we know the concentration of the anode is 0.01 molar, and we have a cell potential of positive 0.06 volts. Now find the unknown concentration.
We know the cell potential is
plus 0.06 volts.
okay. So how do we do it? So this is a concentration cell, so it makes it a little bit easier, right? We're going to do our non-standard cell potential as E cell is equal to E cell naught plus RT over NF natural log of Q, right? Our Nernst equation, our non-standard cell potential equation. In this particular case, what's that? Minus, sorry, that is correct. In this particular case, because we're using a silver-silver cell, we know the standard goes to 0. We know that the N value is 1. I assume you want to do this at 25 degrees Celsius.
Sure.
That goes to 298. So then we plug in all the things we know, and we're going to have 0.06 is equal to 8.314 times 298 divided by 1 times 96485. Natural log. This is the part we have to be careful about. A lot of people get the Q value wrong, myself included, because somewhere in the textbook they're like, oh, just do anode over cathode, right? And that always messes me up. It's a nice shortcut when we've got simple cases like this, but when we have more complicated things, it doesn't work as well. And that's because our Q value, the reason it works for anode over cathode is if you've only got one ionic solution in the anode and only one ionic solution in the cathode, and they're both the product of the anode or the reactant of the cathode, it works out fine every time, right? But if we have something that's even slightly more complicated, if it's a 1-to-2 ratio, anything like that, it's ruined. So I always, to make sure I got my Q value right, I always write down my chemical reaction. Even when it's a silly chemical reaction like this, I've got Ag plus Ag plus with an unknown concentration going to Ag plus Ag plus at 0.01 molarity. And so I can look at this and say, okay, products over reactants, I'm going to have 0.01. They're both coefficients of 1. So it's 0.01 divided by, I'll just leave it as question mark. And now I want to solve for that question mark. So I'm going to go ahead and do 0.06 times 96485 divided by 8.314 divided by 298.
Oh, and then the negative from.
Oh, and then the negative, thank you. I dropped my negative sign again. With the negative to the power of E. And I get 0.0966. I'm going to inverse and times 0.01. And I get a concentration I got 0.1 molarity. It's a little bit different than that. It's 0.103. That's what I got.
Okay.
What did the table suggest we should, or what did the slide suggest we should get?
1.2 molar.
Ooh. Let's see if we made some rounding errors someplace. So let's do. So what I'm going to do is I'm just going to plug that back in.
We also only have the cell potential to 1 sig fig.
Oh, what did it have it on the slide?
To 1 sig fig.
1 sig fig.
Yeah.
Weird. So I'm going to go ahead. Still should be closer than that. I'm going to plug this question mark back in. I'm going to do inverse times 0.01. Take the natural log of that. I'm going to multiply by 8.314. Multiply by 298. Divide by 96485. I get 0.06 exactly. I might have a typo on this line.
Oh, all right.
I probably, so let's do this. What was the concentration I had on the slide?
1.2 molar.
Natural log times 8.314 negative times 298 divided by 96485. Oh yeah, it should have been 0.064. It was just it was rounding on the slide. It should have been a smaller. It should have had more sig figs.
Okay.
It should be 0.064 on the slide.
Got it. Okay.
Again, the place where most people have trouble and make a mistake is someplace in the textbook, or if you go and you watch videos online and stuff like that, they just say, oh yeah, Q is anode over cathode, no problem. Again, that's only for simple cases where it's like metal anode to metal cathode, where you've only got one ion on each side, and it's a 1-to-1 ratio.
Mm-hmm.
If it's a 2-to-1 ratio and you need to square one of them, that doesn't work anymore.
Yeah.
And so it's usually the Q value that's messing people up.
Okay.
You could also just put an ln of Q, solve for Q, and then make that equal to the.
Yeah, as long as you still get Q correct, right? As soon as you
Right.
write down the correct expression for Q, that's true. Most people write the wrong expression for Q
Okay.
in voltaic cells. They do it fine when we're doing other equilibrium, but when they get to voltaic cells, if I don't write down the chemical reaction, I'll mess it up as well. So I write down the chemical reaction from the shorthand notation, make sure I've got it balanced correctly, then write my Q value. Okay?
Thank you.
You bet. I'm going to go ahead and stop recording. I'll answer a couple more